Good morning, my name is Charles.
And my name is Sean. And this morning we're going to present you uh, our project about syngas combustion in round jet burner, which we modeled with COMSOL software. First of all, we want to tell you about our content. So we're going to give you a short introduction, what we did in our project to carry out the simulation. Secondly, we're going to tell you about the syngas, what syngas is generally. Thirdly, we're going to give you a short presentation how we built our model and what assumptions it contains. Fourthly, we're going to present shortly our equations and methods that we use to carry out the simulation. And after this, we're going to show you our simulation results. And finally, we're going to conclude everything. So first of all, the aim of this project was to model the turbulent combustion in our round jet burner, and COMSOL software was used to carry out the simulation. The simulation was carried out by performing it 3 times by changing one parameter in it, and the effects of this parameter to different profiles of this burner were evaluated, and these profiles were temperature profile, carbon dioxide mass fraction profile, pressure profile, and velocity gradient.
So about syngas. So synthesis gas, or short for syngas, is a gaseous mixture of hydrogen, carbon monoxide, and quite often carbon dioxide. It is mostly produced from gasification of carbon-rich feedstocks such as coal, biomass, or any other hydrocarbon. And it's also worth mentioning that there are also other alternatives such as partial oxidation. So syngas is an important intermediate product which is used, for example, in the production of ammonia, hydrogen, and synthetic fuel production.
Now, as we know what syngas, let us see how we actually try to model this round jet burner. So this model consists of a straight pipe which is aligned with a co-flow of air, and the feed exiting from the straight pipe comes into contact with the co-flow air and ignites, which causes combustion of the feed gases. In this model, the inlet flow of the fuel and the oxidizing co-flow of air is kept separate until the point the fuel exits the pipe. Also, this model assumes that the oxidizer, which is the air, and the fuel are fed into the jet burner at stoichiometric amounts in order to achieve a continuous reaction. And this syngas combustion is modeled as an irreversible reaction, and below you can see the reactions that take place in this model.
So about the methods and equations. So the first equation that is seen above is given the production rates, and this is measured in kilograms per cubic meters per second. And these variables that comprise of this equation is the value closure reaction rates and the eddy dissipation model rates. And the mean of these values is actually given this production rate. Now, for the first value within the parentheses, which is the mean value closure rate, it can be measured with the Daum-Coulter number, which is the ratio between the time scale and the chemical scale. And this equation is actually the one straight away below. And then the equation which follows after that, so this eddy dissipation model, this model assumes that both the Reynolds number and the Daum-Coulter's number are high enough for the reaction rate to be only limited by turbulent mixing time scale. And then this equation you can see below is the heat capacity for the mixture. So the procedure, well, this was solved in 3 parts, and the first part is the turbulent and the reactant flow in the jet burner are solved, and then the flow at the outlets is set as the inlets condition for the burner. Then the heat transfer is included, and then the coupled reactant flow is solved based on the previous solution. And the 3 simulations were ran with different jet velocity, and these jet velocities are presented below. So there's 76, which is the default found in the COMSOL application library, and then we varied to 90 to see how it behaves in a higher inlet velocity, and then 62. So the difference between the both are 14 meters per second, to see how they behave at higher velocity and then at lower velocity.
In this slide, you can see the inlet parameters used for the default, for the simulation run with default parameters. And as you can see here, the jet velocity is 76 meters per second. But we decided to present the results of the simulations run with 62 meters per second and 90 meters per second, because from these results the effect of jet velocity in the profiles that we presented earlier can be seen much more clearly. So
here first we have the temperature profile. Now this is the 3D visualization. Now what can be seen, at least just analyzing visually, is that in the left hand side we have at higher velocity, and then in the right hand side we have at the 62, so at the lower velocity. Now just comparing these two, it's kind of clear to see that the temperature profiles remain the same. Now in a sense, what this is telling us is that it doesn't really matter how much the velocity is. I mean, probably there might be some limit at some point, but the temperature profile within the jets stays the same. Now this in a sense does make sense, because for each molecule of whatever feedstock, so in a sense now we're using syngas, but for each molecule of carbon monoxide that is burned, the same amount of energy is released. So if we had a lot, it would just be that the temperature, because it has a specific energy that it released, so in a sense that's specific energy translates to a specific temperature, right? So in a sense this explains why the temperature profiles are the same, because even if we had higher velocity, it would still be in a sense the same amount of energy being released per molecule that is being burned.
In this, when evaluating CO2 mass fraction, we can see that with higher velocity, which is again the left hand side, the CO2 formation is more intense. As can be seen, the red color, which illustrates the amount of CO2 forming, is more intensive in the middle section of this compared to the right hand side. And also we can see that evaluating these two figures, we can see that higher velocities tend to increase the pressure inside the jet or inside the burner more than lower velocities.
And here we can see the CO2 mass fraction. So once again, the left is the higher velocity, and then the right is the lower velocity. Now, one thing that is clear is that the turbulence, the turbulency in the higher velocity is higher. So there is more turbulence, which means that there is more contact between the feedstock or the inlet and then the cold flow, which is why more CO2 is forming, because more reactions are taking place because it's more turbulent. Now, whereas in the right hand side, where the velocity is lower, it's less turbulent, which means that there's less interaction between the cold flow and then the feedstock that is exiting. Also, one thing that is really worth noting is kind of like noticing that the flame is kind of fixed to the exiting of the pipe, which means that there is no lift off, which means that around that area there is more concentration of the exiting feedstock, which means that the flame or the jet is in a sense fixed to a certain position, which is more or less seen also when you light a candle, because in a similar way it has in a sense it has the same effect. So yes, there is more velocity. With more velocity, the turbulency is higher.
And as a conclusion, we could see that there was no visually significant difference between the temperature profiles, no matter what the velocity was. We could see also that CO2 formation was more intense with higher velocities. We could see that higher velocities produced more turbulence around the jet outer shear, and we could see that pressure profile was higher in higher velocities.
Okay, this is the end of our presentation. We thank you very much for your time, and goodbye.
Bye.